Hi everyone, welcome back to our channel. Today, we're going to explore self-reflective-RAG with LangGraph. Self-reflection can greatly enhance RAG, enabling correction of poor quality retrieval or generations. Several recent RAG papers focus on this theme, but implementing the ideas can be tricky. In today's video, we will see the implementation of Corrective-RAG. Corrective-RAG is a part of self-reflective-RAG. CRAG stands for Corrective Retrieval Augmented Generation. It's a strategy that enhances RAG by incorporating self-reflection and self-grading on retrieved documents to improve the relevance and accuracy of generated responses. This video will walk you through each step of the process. Here you can see the image of the self-reflective RAG. This image shows the process. Here, first user will ask the question. Based on the question, we will retrieve the documents using retrieve node. After retrieving the documents, we will grade the documents on the relevance using grade node. And if all the documents are relevant, we will generate the answer using the generate node. And if any documents is irrelevant, we will rewrite the query using rewrite query node and retrieve the information from an external source using web search on the web. And at the last, we will generate the answer using the generate node. So let's get started. First, we need to create virtual environment for the notebook. Now, let's create the virtual environment by following this command. Our virtual environment has been created. First, we need to set up our environment by installing the necessary libraries. These libraries include LangChain, LangGraph, Tavily, and more. You can install them using pip. Here's the command. This command will install all the required packages for our project. Run the cell to install these libraries. Set up the Python environment which we created. To run the cells in Notebook, we need to install ipkernel package. Install the ipkernel package. Pip install LangChain_community TikToken LangChain OpenAI LangChain Hub ChromAd LangChain LangGraph Tavily Python. All the required libraries have been installed. Next, we need to set up our API keys for OpenAI and Tavily Search. These keys will allow us to access the OpenAI language models and Tavily search capabilities. Replace your API key with your actual API keys. To get the OpenAI API key, open your browser and type the OpenAI API key and sign up. Now click on API keys and click on Create API key. Remember one thing, OpenAI provides only some limited calls using the OpenAI API key. After that, to continue to use the OpenAI API key, you have to purchase a plan OpenAI. Copy the API key and paste it into the notebook. To get the Tavily API key, open your browser and type Tavily. Click on the first link. Now click on Get Started. Next, click on Sign in and Log in. Here you will find your Tavily API key. This API key is only valid for 1,000 requests. Copy the API key and paste it into the notebook. Run the cell. Now, let's index some documents that we'll use for retrieval during the RAG process. We'll start by loading 3 blog posts from the web. Here, we load the documents from the given URLs and split them into chunks of 250 characters for easier processing. From LangChain, text_splitter import recursive character text splitter. From LangChain_community, document_loaders import web-based loader. From LangChain_community, vector stores import chroma. From LangChain_OpenAI import OpenAI embeddings. URLs equals https://lilianwang github.io/posts/2023-06-23-agent https://lilianwang github.io/posts/2023-03-15-prompt-engineering https://lilianwang github.io/posts/2023-10-25-adv-attack-llm docs equals web-based loader url.load for URL in URLs docs_list equals item for sublist in docs for item in sublist Text_splitter equals recursive character text splitter. From_tick_token_encoder. Chunk_size equals 250. Chunk_overlap equals 0. Doc_splits equals text_splitter. Split_documents. Docs_list. Next, we add these document splits to a vector store using Chroma and OpenAI embeddings. Vector store equals Chroma from_documents. Documents equals doc_splits. Collection_name equals RAG Chroma. Embedding equals OpenAI embeddings. Retriever equals vector stored as_retriever. This vector store will help us retrieve relevant documents based on user queries. Run the cell. It will take some time. We'll now set up a grader to assess the relevance of the retrieved documents. This grader will score the documents based on their relevance to the user's query. From langchain_core.prompts import chat prompt template. From langchain_core.pydantic_v1 import base model field. From langchain_openai import chat OpenAI. Class grade documents base model. Binary_score str equals field. Description equals documents are relevant to the question yes or no. LLM equals chat OpenAI. Model equals GPT 3.5. Turbo 0125. Temperature equals 0. Structured_LLM_grader equals LLM. With _structured_output. Grade documents. System equals you are a grader assessing relevance of a retrieved document to a user question. If the document contains keywords or semantic meaning related to the question, grade it as relevant. Give a binary score, yes or no score to indicate whether the document is relevant to the question. Grade_prompt equals chat prompt template from _messages. System. Human, retrieved document \n\n document I\n user question. Retrieval_grader equals grade_prompt structured_LLM_grader. This setup uses a language model to grade the relevance of each document. If the document contains keywords or semantic meaning related to the question, it will be graded as relevant. Run the cell. Next, we set up the generation phase using a predefined prompt from LangChain Hub. This prompt will be used to generate responses based on the relevant documents. From LangChain import hub. From LangChain_court, output_parsers, import str output parser. Prompt equals hub.pull, rlm/rag prompt. LLM equals chat OpenAI. Model_name equals GPT 3.5. Turbo. Temperature equals 0. Def format_docs. Return \n\n. Join doc. Page_content for doc and docs. RAG_chain equals prompt LLM str output parser. Here, we define the prompt and the language model that will generate the final response. Run the cell. To improve the effectiveness of our web search, we'll rewrite the initial query to optimize it for better results. System equals you are a question rewriter that converts an input question to a better version that is optimized. For web search, look at the input and try to reason about the underlying semantic intent/meaning. Re_write_prompt equals chat prompt template from _messages. System. Human. Here's the initial question \n question \n formulate an improved question. Question_rewriter equals re_write_prompt LLM str output parser. This setup will help us transform the original query into a more effective one for web searches. Run the cell. If the retrieved documents are not relevant, we perform a web search to supplement our retrieval. From LangChain_community to tools, Tavily_search import Tavily search results. Web_search_tool equals Tavily search results, K equals 3. This tool will allow us to perform a web search and retrieve additional documents. Run the cell. Now, let's build the workflow as a state graph. This graph will define the nodes and edges that represent the steps and transitions in our CRAG process. We will start by defining the graph state and the functions for each node. First, let's define our graph state and the functions for each node in our state graph. From typing import list. From typing underscore extensions import type dict. From langchain.schema import document. Hashtag define the graph state. Class graph state. Type dict. Question str. Generation str. Web underscore search str. Documents list str. Hashtag function to retrieve documents. Def retrieve state. Question equals state question. Documents equals retriever. Get underscore relevant underscore documents question. Return documents question. Hashtag function to generate response based on documents. Def generate state. Question equals state question. Documents equals state documents. Generation equals RAG underscore chain. Invoke context documents question. Return documents question. Generation. Hashtag function to grade the retrieved documents. Def grade underscore documents state. Question equals state question. Documents equals state documents. Filtered underscore docs equals. Web underscore search equals no. 4D in documents. Score equals retrieval underscore grader. Invoke question. Document d.page underscore content. Grade equals score binary underscore score. If grade equals yes. Filtered underscore docs dot append d. Else. Web underscore search equals yes. Return documents filtered underscore docs question. Web underscore search. Hashtag function to transform the query for better web search results. Def transform underscore query state. Question equals state question. Documents equals state documents. Better underscore question equals question underscore rewriter. Invoke question. Return documents question. Better underscore question. Hashtag function to perform web search if documents are not relevant. Def web underscore search state. Question equals state question. Documents equals state documents. Docs equals web underscore search underscore tooled. Invoke query question. Web underscore results equals \n. Join d content 4D in docs. Web underscore results equals document. Page underscore content equals web underscore results. Documents append web underscore results. Return documents question. Hashtag function to decide whether to generate response or perform web search. Def decide underscore to underscore generate state. Web underscore search equals state. Web underscore search. If web underscore search equals yes. Return transform underscore query. Else. Return generate. We have defined several functions that handle different steps in our workflow: retrieving documents, generating responses, grading documents, transforming queries, performing web searches, and deciding the next step based on the grading result. Run the cell. Next, we'll set up the state graph by defining the nodes and their transitions. From LangGraph to graph import yendi, state graph. Hashtag create the state graph. Workflow equals state graph, graph state. Hashtag add nodes to the state graph. Workflow.add underscore node. Retrieve. Workflow.add underscore node. Grade underscore documents. Workflow.add underscore node. Generate. Workflow.add underscore node. Transform underscore query. Workflow.add underscore node. Web underscore search underscore node. Web underscore search. Hashtag define the entry point of the workflow. Workflowed. Set underscore entry underscore point. Retrieve. Hashtag add edges to the state graph to define the transitions between nodes. Workflow.add underscore edge. Retrieve. Grade underscore documents. Workflow.add underscore conditional underscore edges. Grade underscore documents. Decide underscore to underscore generate. Transform underscore query. Generate. All. Workflow.add underscore edge. Transform underscore query. Web underscore search underscore node. Workflow.add_edge web_search_node generate. Workflow.add_edge generate end. In this setup, we define the entry point as the retrieve node and specify the transitions between nodes. Depending on the grading result, the workflow will either proceed to generate a response or perform a web search to supplement the retrieved documents. Run the cell. Finally, we compile and run the workflow with an example input question. This will demonstrate the full CRAG process in action. Let's compile the workflow and run it with a sample question. #compile the workflow. App equals workflow.compile. #define the input question. Inputs equals question. What are the types of agent memory? #run the workflow and stream the output. For output in app stream inputs. For key, value in output.items. Print f node key : print \n #, print the final generated response. Print value generation. Here, we compile the state graph into an executable workflow and define an example input question. The appStream method runs the workflow and prints the output at each node, showing the process step by step. Finally, we print the generated response. Run the cell. As we can see in the output, the workflow processes the input question through multiple nodes, retrieve, grade_documents, possibly transform_query, web_search_node, and generate. Each node prints its name, and at the end, we get the generated response. Let's do a quick run through the process with another question to see the workflow in action once more. We'll use the question, how does the alpha-codium paper work? And run the workflow again. Again, the workflow processes the input question through each step, and we get a detailed response at the end. And there you have it. We've successfully implemented and run a Corrective-RAG using LangGraph. This workflow enhances the retrieval and generation process by incorporating self-reflection and self-grading, ensuring more relevant and accurate responses. I hope you found this tutorial helpful. Thanks for watching, and let's meet again in the next video.